Hello, pre-calc students. This is Mr. Beck. Today I'm going to be talking about the first half of 5.4 to 5.6. 5.4 is about logarithmic functions and how to work with them. And then 5.5 is some properties of logarithms, and 5.6 is solving equations using logarithms. Now, the reason why I'm lumping all three of these sections together is because I'm a firm believer the logarithms are a very, very tough idea to understand because they're a little bit more abstract than what we're used to. We're used to very concrete examples of addition, subtraction, multiplication, division. Working with logarithms is working on the exponential level. Because of that, it's not quite as easy to see, and so there's a lot of practice that needs to be done to really truly understand what's going on. So where we're going to go and how we're going to start is, what is the logarithmic function? A logarithmic function is defined as the inverse of an exponential. So it's the inverse of an exponential function. Because it's the inverse of an exponential function and the y is in the exponent, what we do is we rewrite it in this logarithmic form that I have right here. Now, the domain of a logarithm is all our numbers greater than 0, and a lot of that has to do with, if you think about the graph of an exponential function, which looks like so, graph of the exponential function, if we invert it, is going to now have a vertical asymptote, and it's going to open in that manner. Not the best inverted relationship, because that really should have been over here. Work with me on that one. So we are working with the inverse of an exponential, which is why domain is going to be greater than 0. Now, defining them as inverses is going to be my focus. For instance, if you look at log base 3 of 81, now one of the things I want you to do every time you see a logarithm, I want you to think about it in a certain format. You don't want to say just log 81, because there are operations that are going on there that you want to make sure that you have in mind. We're taking log, yes, this is the logarithm, so we're going to take the log with a certain base of a certain number. So log base 3 of 81. Now, what the meaning behind this logarithm is, we're trying to find the exponent, not just any exponent, because 81 is 9 squared, 81 is 3 to the 4th, 81 is the square root of 3 to the 8th power. So it's not just any exponent that we're trying to find. We're trying to find the exponent that comes from the same base, which is why this base of 3 is so important. So if I can rewrite 81 as 3 to a certain power, log base 3 of 3 to the 4th, this is where the inverse relationship comes in. The logarithmic base and the exponential base undo each other, and we get that exponent of 4 of what we want. So when we look at this problem, can we rewrite 8 so that it has a base of 4? So sure, 8 and 4 both have a common base of 2. So our first step is we want to write it with a base of 4. So how do we get this 4 down to a base 2, which is what they share, and that's where the square root comes in. And then we have to cube it. So the square root of 4 is 2, 2 cubed is 8. So everybody should agree that 4 to the 3 halves is 8. I'm not saying it's easiest to find, but we have to take the steps to think through it this way. So the square root of 4 is 2, 2 cubed is 8. Now that the logarithm and the exponential have the same base, we're left with that 3 halves, which is the exponent of what we want. So log base 1/3 of 27. Well, let's rewrite 27 as 1/3 to a power. Well, how do I turn 1/3 into a 27? Well, first we have to reciprocate it, which is where the negative exponent comes in. So now that 1/3 reciprocates to 3, 3 to what power is 27? 3. So log base 1/3 of 1/3 to the negative third is negative 3. Same thing here. How do I turn 64 into a base square root of 2? Well, square root of 2, if we square it, becomes 2. And then if we take that to the 6th power, it becomes 64. So now by exponent rules, we can multiply these two together to be the 12th power. So log base square root of 2 of square root of 2 to the 12th is 12. Again, because logarithms and exponentials invert each other. Now we have this thing that looks like an ln. So this ln really represents what's called the natural log. So the ln is the natural log. Now the reason why it's ln instead of nl has to do with most math was not created in America. And if you look at a lot of the Romance languages, which is where a lot of math was formulated, then what they do is they use their verb before the noun. Sorry, and they use their verb after the noun. We use our verb before the noun. So they say the logarithm, which is natural. But anyway, history lesson over. So log base e, which is what the natural log is, log base e of e to the 5/6 is simply 5/6. So how do we convert to the invert form? Now, in Algebra 2, you most likely learn some inversion formula, which is not wrong. I really don't like to focus on that because that's just a formula saying, hey, move this here, move that there. There's not really a whole lot of explanation of why it is. Most students who I ask, why does that work? They're like, I don't know, I was just told to do that. So this is where I want to really focus on more of like an active mathematics. This is what I call passive mathematics because you're just following some formula and hope you're doing it right. Active mathematics is saying, hey, I can take a certain operation on here because math is all about using inverses. The inverse of addition, subtraction, the inverse of multiplication is division. We can undo things by using the inverse properties. So how do I undo a 4.5 to the x? Well, just like we saw up here, if we can rewrite it so that we're taking the logarithm of that exponential, then we're going to be able to solve it for x. So what undoes the exponential base 4.5? A log base 4.5. So I will take log base 4.5 of both sides. So when I take log base 4.5 of both sides, then these do invert each other and we're left with x. And over here we have log base 4.5 of 12. So part B, how do I invert the 12th power? Well, we invert the 12th power with the 1/12th power. So if I take the 12th root of both sides, I get this. Now, this problem was written, and really this is a power function. The inverse of a power function is the reciprocal power. If I wrote this in a logarithmic form, this logarithmic form, I could take log base x of both sides. So by taking log base x of both sides, I will have this expression. So we're left with 12 because the log base x and the base x here undo each other. So we have 12 equals log base x of 73. Now, these two expressions actually have the same meaning. Now, log base x is not something that we really think about because we know how to solve that using some exponent properties. That's why if we want to solve for the exponent, we usually have that as the variable. But the reason why I have this problem in here is because I want to show you what the meaning of this logarithm is in a format that we're more familiar with. For part C, now we're starting with a logarithm. So what we're going to do is we are going to invert the log base with an exponential base. So I will take 8 to both sides. So it's really saying I'm taking 8 to both sides. By doing that, really what we do to one side of an equation, we can definitely do to the other side of the equation. But by doing this, we are actively undoing the logarithm. So 8 to the log base 8 gives us just what's called the anti-log. What's inside that logarithm is called the anti-log. So we're just left with what's left inside, the x. So x is 8 to the 34th power. Now what I like about this problem is 8 to the 34th power is an absolutely huge number. Because that's such a big number, then I would rather work with 34. So the whole point of logarithms is to allow us to work with extremely large numbers or extremely small numbers on a much more normal level. So going back to what is a logarithm and how to work with a logarithm, just to give you that full understanding of what it is and how it works, I'm trying to give you overall connections to past knowledge that you have. And this one, how do you undo the natural log? Since that's log base e, we undo it with an exponential base e. So I am taking e to both sides. So e to both sides. And now the e and the natural log undo each other. We're left with 35. And on the other side, we have e to the x. The properties of logarithmic functions. Domain is from 0 to infinity, like we mentioned. Let me go ahead and throw that generic graph up here. So we have the vertical asymptote. So the domain goes from 0 to infinity. The range is all real numbers. Usually the x-intercept is at 1. That's unless we translate and so forth. So that's 1, 0. And the reason why that's 1, 0 is because the exponential function will always go through 0, 1. There are no y-intercepts on this one because the domain is just positive numbers. Increasing 1-to-1 function, we hope it's 1-to-1 because that means it has an inverse. And since it is an inverse, we know the inverse is an exponential. So if f of x is decreasing, our base is going to be between 0 and 1. Notice that the base is only going to be positive numbers. That was true for exponentials as well. And then we contain these points. These are the 3 points that I typically like to graph off of. So now we're choosing the points 1 over a because log base a of 1 over a is -1. Log base a of 0 is 1. Log base a of a is 1. So by choosing those 3 points, we can make the 3 key points on a logarithmic function, which will look something like that. And all logarithms are smooth and continuous. That's kind of a preface for what we do in calculus next year. So natural log, as I mentioned, is ln, so our log base e. The common log is just written as log of x. This common log, and I say in America only, because in Europe, a lot of times, if you just wrote the log of x, they actually think that it's the natural log of x, just because a lot of mathematics were developed there. The common log is something that's used in the financial world. So moving along, find the domain in the following. The way that we find the domain in the following is we know that what's inside has to be a positive number. So we begin by saying what is inside is greater than 0. So what's inside that logarithm or the anti-log has to be greater than 0. 5 minus x is inside. 5 minus x is greater than 0. And then if we solve, we get from -infinity to 5. For this problem, we now have a quadratic inside that logarithm. That quadratic inside the logarithm, we set that quadratic greater than 0. This is a throwback to chapter 3 where we solve quadratic inequalities. We know that we have to factor and determine where the regions are positive, which if I do the number line test, then the regions are positive before -1 and after 3, which is why that is our overall solution. For part C, we now have a rational expression inside. So here's our chapter 4 inequality review. So we set what's inside greater than 0. And once again, if we do our number line test, we know that 7/2 is the 0, 5/3 is the vertical asymptote. We determine where it's positive and we get our solution that way. Now for our next set of problems, we're actively finding the inverses of all these functions. So to find the inverse, we're going to be using that solving technique that I was just doing a moment ago, where that solving technique is, well, first we switch the x's and y's because when it comes to solving any kind of equation, or solving and finding the inverse, we switch the x and the y. So here's our y, switches with the x. Here's our x, switches. And now to solve, solving is undoing the order of operations. And most people, when they think order of operations, they think PEMDAS. What's going on is the logarithms and the exponentials actually work together because they're inverses of each other. Just like multiplication, division, and addition, subtraction are inverses. So switch x and y, and now we have to undo the 7 by subtracting, and then undo the exponential base 6 by taking log base 6 of both sides, and then adding the 4, and we get that expression. One of the things that I like to point out is what's the domain of this, and we know that what's inside has to be greater than 0, so it's 7 to infinity, and the range is all real numbers. Now, if we go back to the exponential function, and here's our 5.2 review, that these invert each other as well. So domain and range, or domain becomes range, and range becomes domain. And that's one way that we could check all of these problems. For instance, on B, this is an exponential function, so horizontal asymptote. We know that it's going to look like that. So our domain is all reals, and our range is from -3 to infinity. So when we get to the end, those two will invert each other as well. Now, how do they invert each other? We start by switching x and y, adding 3 to both sides, undoing the 4 by dividing by 4 next. And then how do you undo the exponential base e? By taking the natural log of both sides. So the natural log of the left side and the natural log of the right side, they undo each other, and we're just left with what was in the exponent. Then we subtract 1 and divide by 2 in order to solve fully for y. Now I prefer you to write it as 1/2 times each of those terms rather than all that divided by 2. All that divided by 2 gives you a fraction within a fraction, where the 1/2 times each of those does not. Now, if our problem starts off as a logarithm, domain is from -8 to infinity because that's what makes it positive. You notice when we invert, the range of it will become from -8 to infinity as well because that range is an exponential function. Switch x and y one more time. Switch x, switch y. So we undo the -6 first by adding 6. We undo the -2 next by dividing by -2. Now, how do we undo the logarithm? With 10 to both sides. So 10 to both sides. And then what's left? We have to undo the +8 by subtracting it. For part D, switch X and Y. We have to undo the 5, then undo the 3. And I did that in one step. We started by subtracting 5, then dividing by 3. Now, how do I undo the natural log? I take e to both sides. So e to the left side is just that. E to the right side is 2y. And then we divide by 2, or I like to always say multiply by a half. Now, this exponential function, that's +0. So our range is from 0 to infinity, where the domain of an exponential is all real. Now, how do we graph logarithms? To graph logarithms, I'm going to go back to those 3 key points of what I was looking for. Those 3 key points are 1 over the base, 1 in the base. So I want you to always think about it as log base 3 of x. To do log base 3 of x, I want to know what's log base 3 of 1/3, which is -1. Log base 3 of 0, not 0. Log base 3 of 1, which is 0. Log base 3 of 3, which is 1. And if we can find x values that are going to give us those 3 y values, they tend to form the most important part of the curve for us. And really, we like to see where that curvature occurs because it helps us visualize better. So I do look for those 3 points. Now, there are some approaches like in Algebra 2 where they had you actually do the inverse, find the x values -1, 0, 1, and then re-invert. That's what you see that I did here. It shows a nice graphical relationship between the exponential function and the logarithmic function. Now, for me, that tends to be a little bit more work than what I normally want to do, especially when I can think through some of these a little bit more efficiently. Well, what happens if we can't think through it quite as efficiently? Well, what we could do is we can say, I want my 3 x values or whatever goes inside here, I want those to be 1/4, 1, and 4, which I have in exponential notation. So what I could do is set what's inside equal to those. Now, I don't encourage this if you don't have to, but at the same time, if you cannot see what numbers those should be, go ahead and do it. Set what's inside equal, let me write that down, set what's inside equal to 1 over a, 1 into a. And then when I do that, you see I actually have my math here. I have log base 4 of 1/4, which is -1, log base 4 of 1, which is 0, log base 4 of 4, which is 1, creating those 3 points. Now the vertical asymptote, which sadly I've not talked enough about, is where you will have the log of 0. So if you wish, you could take that one step further and say, what makes what's inside equal to 0? And in doing so, you get an undefined value, which translates to a vertical asymptote. Last but not least, I have this problem. Now, 4 minus 2x, because 4 minus 2x is starting to get a little bit more complex than what I want, I could set what's inside equal to 0 and solve it that way. Set what's inside equal to 1/2, which is what this is. Set what's inside equal to 1, which is what this is. Set what's inside equal to 2, which is what this is. Now you can go even further. What's inside equal to 4, which is that. What's inside equal to 8, which is that. And the reason why I know those values is because those give me clean y values that I can graph. Now, in the end, I have a graph that looks like this, and it's like, oh no, why does it look that way? Well, it looks that way because this 4 minus 2x has 2 different transformations. If we factor out the -2, it becomes x minus 2. So there should be a shift to the right 2 and a reflection over the y. And hopefully you like that shocked face. Oh no. Anyway, now solving logarithmic equations one more time. It's all about the same approach as how we solved inverses or how we found our inverses. So how do I undo a log base 2 with an exponential base 2? I take 2 to both sides. Then I get what's inside the logarithm or the anti-log equals 2 cubed, which is 8. Solving for x, we get 6. We can go back and check, but the most important thing is if we understand what the domain is right from the beginning, we know whether we get the correct answer or not. Problem number 9, how do I undo a log base x? By taking x to both sides. So x to both sides gives me 1/16 is x squared. Remember, the whole point is these undo each other, and we're just left with the anti-log. Now, if I solve this for x, I get two distinct x values. But if you remember, a has to be a positive value, or the base has to be a positive value. Therefore, only the positive 1/4 will work. Problem number 10. Now, I like to take this problem and say, wait a second. I know that 16 is 2 to the 4th power. So what I can do is multiply those exponents together, which is what I do there. So that's 2 to the 4th, or 4 times 4x minus 2. Now, these will undo each other because they're inverses of each other. We're left with 16 minus 8 equals 6x. So x is 4/5. Problem number 11. Begin by dividing both sides by 4. Remember, undoing all the order of operations. Now I have to undo the exponential base 10 with a log base 10, which of course we don't see because it's a common log. So take the common log of both sides, and then what's inside equals the common log of 305/4. So just add 2 to get our overall answer. Problem number 12, how do we undo e? We undo e with the natural log. So undoing them, we get 6x minus 7, and then the natural log of 1/8. So add 7, divide by 6, and I get this expression right here. And problem 13. Problem 13 looks a lot more complicated. And so as it looks more complicated, one of the things that I do encourage you to do is say, wait a second, 216 is 6 cubed. So really that right side should be 3. Now we add 7 and divide by 5. We get e as this negative number. And so when we take the natural log of both sides, which is what I'm showing here, the natural log of both sides, we get this as the natural log of negative 4/5. We are not able to take the natural log of a negative number. Therefore, these two will never actually be equal to each other. All right, okay. So then we get into solving some logarithms. And now when we're solving some logarithms, one of the things that we're going to do is pretty much use the properties that we started developing, and we're going to establish a few more problems, or at least a few more properties. The first property, our first two properties are ones that should be well known at this point. Now what I have is 1 and 2 on this list. As 1 and 2 on that list, those show the whole inversion process. So this shows that these are inverses of each other. Property 3, which I have right here, so the multiplication of my anti-log turns into addition of the logarithms. That actually corresponds to what we did in with exponential functions. So this corresponds to the idea that if we have like 3 to the x times 3 to the y, because those are the same base, we can add the exponents. Well, logarithms are exponents because we're working on the exponential level. Since those are exponents, we are adding the exponents by multiplying the anti-logs together. And then 4 is division. So once you understand 3 a little bit better, 4 ends up being the same thing. Division of those logs means subtraction. So 3 to the x divided by 3 to the y, division of the bases, division of the anti-logs, turns into 3 to the x minus y, subtraction of the exponents, or subtraction of the logs. Now what I have over here are just some examples that we randomly made up in class. But what I'm doing with this is I'm really working backwards. If I'm adding 2 logarithms together, I can turn them into 1 log of the multiplication of them. Dividing my 2 logs, dividing my anti-logs, actually I have this kind of in reverse. So subtracting the logs will turn into division of those anti-logs. Now, this is the direction you took it most of the time in Algebra 2. I want you to make sure that you know how to work backwards with this as well. Then property 5. Property 5 says, hey, we can bring that exponent out in front and we're happy. But why does that work? This really refers back to property 3. 5 cubed is 5 times 5 times 5, which we could break into 3 individual logarithms like so. But since those are all the same term, we could say we have 3 of those exact same terms. Because of this, what it shows is that exponent can be brought out in front and the property holds true. And one of the things we have to be careful of is, even though the property holds true, the domain has to be what you start with. So if you notice, this expression is a quadratic. So this is similar to the practice problems that we just did a moment ago. The domain of that expression has two different regions where it's working, where in problem number 3, our domain has to be x is greater than 0 for this one, and x is greater than 2 for this one. So the overall domain for this expression is really the intersection of both of those domains. The intersection of both of those domains is x is greater than 2. So this domain is what we're going to follow, where this domain was x is greater than 2 and x is less than 0, or x is less than 0. So this domain is a bad domain because this is what we start with. So on this one, this domain of x is greater than or equal to 5, actually just greater than 5/3. And then or x is less than -7/2 is the domain of this expression. So if we use the properties, these properties actually are even more limited, but the overall domain of the function is going to be that, assuming that we could plug it in individually. Let's go into some examples. This example number 1, pretty similar to what we already did. So write it as the power over the root, so e to the 5/2. Natural log of e to the 5/2 is just 5/2, again, because those invert to each other. For part B, what we have is I've turned this into one logarithm. So I have 3 distinct terms. Because I have 3 distinct terms, I'm going to turn into one logarithm. So where we have a positive term, we are going to have that in the numerator, that anti-log in the numerator. This is a negative term. So it's a negative term, so that 216 goes in the denominator. This one right here is a positive term, so that goes in the numerator. And now I just went through some multiplications. Most students do this by calculator, which is okay. But in the end, we get log base 6 of 2. C, with C, I did this in 2 different approaches. In fact, I had students in class who took this approach, which was great. And now log base 12 of 144 is 2 to get 6x. What we could do is we could turn it 144 into 12 squared, multiply those together, and now these undo each other because they're the same base, and we get 6x. What I love about logarithms is logarithms allow us to be so flexible with how we do the math, and it's beautiful. This next example, use the given logarithms and properties to write everything in terms of a and b. So I take the natural log of 2/3. And that's division of the anti-logs, so I subtract the natural logs, so that turns into a minus b. Natural log of 3 cubed over 2, the natural log of, which is 27. So 3 natural log of 3 minus natural log of 2 turns into 3b minus a. Natural log of 3/4 to the 1/5 power. So I just went through a process here. I don't think it's the most efficient process that I've walked through, but first, write it as an exponent. Next thing I did was I brought that 1/5 out in front. And now we break up the natural log into the 2 different quantities. And 4 is 2 squared. So I could write what's inside the quantity as natural log of 3 minus 2 natural log of 2. Multiplying everything by 1/5. So 1/5 of b minus 2/5 of a. The reason why this is important is kind of a little historical. That if I take the natural log of 2 plus the natural log of 3, this becomes the natural log of 6. So if I know what the natural log of 2 and the natural log of 3 are, I actually can add those 2 numbers to get the natural log of 6. Same thing, that if I wanted the natural log of, say, 8 as the natural log of 2 cubed, or 3 natural log of 2's. So I know that expression is 3 times 8. So once we know the decimal values of all of our prime numbers, we can actually find the natural logs of any of those values pretty easily too. So moving on, and then my notes really went through this page. So, or at least the first day's notes went through this page. The next step is to expand. And when I say expand, if I have this as one logarithm, can I turn it into multiple logs? And the answer is yes. If I know how many factors are inside the logarithms, it tells me how many logarithms I have. The numerator becomes a positive log. The denominator anti-log becomes a negative log. And this one can simplify. For B, I have two distinct factors, so I can break that up into two terms of natural logs. And then that cycle one simplifies to x. This one, we brought the exponent out in front. For part C, two factors, so I can turn it into two logs. And now that I have a denominator, that's a negative log. And now we can bring the exponents out in front. So 4 times the log base 5 of x minus 2 times log base 5 of x minus 4. And if we can expand, we can certainly condense, bring it back together. So when we condense, log base 4 of z, if I take that 2 and bring it up as an exponent, looks like so. Bring the x up as an exponent, looks like so. Now I have two terms of logarithms. I can join them into one big logarithm with the same base. And that one big logarithm, we know that z squared is in the numerator, 3 to the x is in the denominator because of the negative. For part B, how many terms do I have? 1, 2, 3. 3 terms, positive terms, which would be the first and the last. Those anti-logs go in the numerator. And then the negative logarithm, that goes in the denominator. And if we multiply by x over 4, we can simplify into that expression. For part C, 1, 2, two logarithms separated by addition. So that means I'm multiplying. If I multiply and I FOIL these through, I will get this expression. So really, this is the difference of squares. They just look like square roots. So the difference of squares, when I simplify, don't forget to distribute that negative to both. So log base a of 1, which is 0. So all of that gives me 0, which is kind of beautiful. For problem number 5, 5a, first thing that I look for is what's the domain. And the combined domain, this one is greater than negative 15, this one greater than 0. So if I have negative 15 here and I have 0, the overlapping of both of those domains, which is the darker one, is going to be greater than 0. Join those together in multiplication. Take 10 to both sides. And then when we do that, we get that equals 100. So 10 squared, which is 100. Now this turns into a quadratic. So here's some chapter 3 review for us. For part B, domain, x has to be greater than negative 4, x is greater than 2. So that's the more restrictive domain, so that's the overlapping of it. Now, I brought the logarithms to one side and then combined them together into one logarithm, followed by how do I undo that log base 6? Of course, with the exponential base 6. So I have what's inside equaling 6. Cross multiply both sides, and I will get this expression, which gives me x is equal to 16 fifths. For part C, first step I did was I took this 2, brought it up as an exponent, then combined these into one, combined these two into one, after of course I brought the 2 up. Then I take 3 to both sides, and 3 to the log base 3 undoes each other. We're left with the anti-log of x over 25. And then on the right side, we have x plus 1 over 100, and now we solve this linear equation. For part D, I like part D a lot because part D honestly brings back some 5.2, really 5.1. 5.1 talked about composition of functions. So what I have here is actually a quadratic function. We have something squared minus 3 times something, and then let's say minus 4 equals 0. So this is a quadratic function, but a logarithmic function is embedded in that. So this is a composition. Now, to make life easier, we could do what's called a u substitution. Let's let u equal to that logarithm. So now we have u squared minus 3 times u equals 4. And we solve that by factoring. And once we factor that, we could set u equal to 4 and u equal to negative 1, which is all great, except I don't care about u, I care about x. Well, since u is log base 2 of x, I can resubstitute. So resubstitute that in for u. And take 2 to both sides, get 16. Take 2 to both sides, get 1/2. So hopefully you appreciated the first portion of these notes. And shortly you'll be seeing the second portion of the notes. Have a good day.